This is the Amp Hour Podcast, released June 3rd, 2018. Episode 395, an interview with Luke Valenty. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Luke Valenty from Tiny FPGA.
Welcome, Luke. How you doing?
I'm doing great. How are you doing?
Good. Well, this is an early... I'm not used to recording the morning. We're recording the morning this time, and I'm a little more caffeinated than normal, so if I ask crazy questions, I'll blame it on that.
Likewise.
Yeah, okay, good. So we're going to be talking FPGAs, so should people be caffeinated themselves to listen to this? I mean, should people be excited about FPGAs?
Oh my gosh, yes. You should be very excited about FPGAs.
Why should people be excited about FPGAs?
Okay, so some background. I was just at Maker Faire, Bay Area, and this was my first time ever exhibiting at a Maker Faire, which was awesome. And on the very first day, on Friday, before it started, I saw a tweet from Arduino that made my heart sink at first, and it was that Arduino was releasing their own FPGA board.
Right.
And it has kind of a smallish form factor. You could put it on a breadboard. It's got some pretty cool features. And inside, my first reaction was, oh God, what am I doing this for now? I'm going to be crushed by Arduino. But then, my more practical and realistic self kicked in and reminded me that, there's lots of different reasons, we want FPGA boards, and people have different requirements and things that they want to do. And it's actually fantastic that Arduino is getting into it. Because number one, it's a recognition from a very large, influencer in the maker community that FPGAs are important for makers and hobbyists, and they're really, really useful. So it's kind of a confirmation of what I've been working on and doing here, and what other people have been working on with with FPGAs for makers.
I think I'm going to challenge you on that one. I don't think actually most people need them. I'm personally very interested in them, but maybe you could explain to me when you think people should start jumping into FPGAs.
Okay, I've had a lot of practice because of Maker Faire.
Yes, good.
And if you look at Arduino project and you look at some of the libraries, there's a lot of bit banging libraries. And there's a lot of bit banging libraries for things even as simple as serial ports for UART. Because for whatever reason, some people want a lot of serial ports. I haven't figured out exactly why they want so many serial ports, but they want a lot. And they want the maximum baud rate available. And if you're using software serial, depending on the board you're running on, you're only going to get 9600 or a little bit more baud. And it's not always very reliable. So
and they're using it for debug too at the same time, right?
Yeah, exactly. You could be using it for debug. And the more of these software serial ports that you add up, the less CPU time that you have for your actual, task at hand. And so if you use an FPGA board, you can implement a soft microcontroller on it, and you can specify exactly how many serial ports you want. Not only can you do that, you could also set it up so that if you have a sensor on each one of those serial ports, you can have dedicated hardware for each one of those ports that will pull that sensor, or that will record the data from the sensor and put it into a register, so that your main program can be offloaded and not have to worry about those periodic tasks. Yeah. So you could not know a single thing about Verilog, and with the right software and tooling, yeah, exactly, which is, almost everybody that I talk to at Maker Faire. And with the right tooling, though, you could put together a microcontroller that does exactly what you want. And so that's a major use case that I think is useful to anybody that uses microcontroller boards today, is being able to put together exactly the peripherals that you want and use them in your project.
Yeah, because I think about it at the beginning, it's almost like you have people that, and the reason that I push back on it in the first place, normally I wouldn't, because I really do like FPGAs, but I think that the thing is, people coming in maybe 10 years ago, or maybe even more recently, it's like, well, you should really learn the constraints of the system first, because if you jump right into, let's see if I can make an analogy. If I'll use one of my favorites. Like if you were gonna like use piano, but your pinky didn't stretch to the one of the keys, right? This is what you're kind of saying is like, well, you'd move one of the keys to make it a little bit more convenient for that person. And so what I'm saying is that it kind of makes that person not as adept at practicing and stretching to get to that key on the piano. And I think that there's some value in that. But I think pretty quickly the idea is that the key needs to actually be moved. For certain tasks, the key actually does need to be moved, and there's valid reasons to move that key.
Oh, yeah.
So my fear is always just that the people jump right to that and think that that's the solution right away. And I don't think that's the case, but I think that quickly it could be, right?
Okay, so I want to make sure I understand your metaphor. Could you make it more concrete? Moving the key corresponds to...
Oh, so like actually rearranging the piano keys. That's what I meant. Sorry.
Yeah. So and that corresponds to what?
Not learning how a standard piano layout is, right? So that's and in this case, to go back to the normal example, right? So a lot of people in the Arduino community use like an Atmel 328, Atmega 328 rather, and like learning register sets and learning that there are constraints on hardware and that kind of thing. But I guess you were kind of saying that they do it with software anyways, right? So that maybe that wasn't a good example.
Yeah, I mean, in the Arduino environment, there's a lot of abstraction between the hardware and being able to use it. And it's a double-edged sword. So there's positives and negatives to that. On the bright side, a lot of sketches that aren't too complicated can be ported from one board to another without too much fuss.
Right.
If you are going to using the registers immediately of a particular microcontroller, when you port it, you're going to have to port all of those specific registers over to whatever features are on the target board.
Oh, interesting. Okay. So you're saying that an FPGA and the flexibility of it allows you to have a standardized register set that people are used to dealing with, but you can...
you could do that if you wanted to. I'm not necessarily advocating that. I like the idea of having the abstraction at the software level, as long as it's not... adding too much overhead. But on an FPGA, you could have, and this is what would happen if you have a good tool for creating SoCs, like MyGen. You're going to end up having a few different IPs that most people are using. So standard IPs for something as simple as a UART. Now, no matter what your CPU is that you might choose for that SoC, you might end up using the same UART that everybody else is using because it's really well supported and it has the features that you need. And so, regardless of the other configuration of your microcontroller, you're going to have the same UART. But I wouldn't expect that you would still be programming the registers directly for that UART. You probably would still want to use a higher level driver to talk to it, just because it's simpler and you can get things done faster.
Yeah. Okay. Interesting. Cool. Well, so you're saying that you think that FPGAs are a good starting place for beginners though too? Is that kind of what you're getting towards? Yeah,
actually, they can be, and it depends. Okay. It depends on what you want to do. Yeah. So, if you want to learn FPGAs and you buy a Xilinx dev board or an Altera dev board, okay, then you end up downloading Vivado, which is 30
Good luck
gigs.
With that. Right.
And it is a very powerful tool, but I tried it for the first time not too long ago, porting one of my projects over, and it has a very interesting take on user interfaces. There's some interesting modes that it has between, doing design and implementation, and options appear and disappear depending on what mode you're in, and it's not the easiest thing to learn how to use.
Yeah.
It's not like a software IDE where, you can press a couple buttons and do exactly what you need. And that's partly because so many people use software IDEs. It could be even on the order of like 100,000 or 1 million times more people use software IDEs than they use tools for FPGAs. So if you use that, that's not going to be so great for a beginner. It's going to be pretty difficult, and just the mechanics of getting the software installed, getting a license on your computer, and generating the bit stream is actually complicated. On the other hand, there's a tool called iStudio, written by a group of people that go by FPGA Wars. It's a parody on Star Wars because the creator is a huge Star Wars fan. He's Obi-Wan on Twitter, with a JUAN.
Got it.
It's mostly a Spanish-speaking community, and they're all mostly in Spain.
Cool.
But it's pretty fantastic. They have an incredible set of tutorials for people that really wouldn't necessarily have any experience even programming. Yet they have people doing projects on FPGAs using iStudio, which is sort of a schematic entry tool, where you can do schematic entry, and then if you want, you could also insert Verilog modules. And then they have tools for sharing the modules and creating collections of modules and components that other people can use and remix. Mm-hmm. And so I've seen some really interesting projects come out of that, like a remake of Pong, with no microcontroller. I've seen Space Invaders, and I've seen simple things like, just somebody learning how to blink an LED for the first time on any dev board. Never mind the fact that it's an FPGA dev board.
Right. Yeah, I think that's one of the indicators of a dev board toolchain working in the first place, is getting that first blink, right?
Yeah. Oh yeah.
Okay. So you think though? So the idea though is that you think it is a good path forward for people that are not that are not more experienced. You think it's okay?
I think that the major thing that we need is the tools. We need tools for people that can do things like create your own microcontroller and then take care of everything behind the scenes so that it works. We need tools like iStudio, where you can do schematic entry and you can visually create digital circuits and put them together. And we need the open source tools that Tim and Clifford and others are working on, because these open source tools are the ones that, like the open source toolchain, that's sort of the genesis of all of this. If you can release your toolchain open source and people can download it and they can redistribute it without having to get a license file, without having to go to a separate website, and then they can remix it in whichever way they want, what you get then is a really nice diversity of solutions on how to use it. So iStudio is one of those. It's great for beginners because all they need to do is download iStudio. That's it. Okay. They don't have to go to any vendor website to download other tools. They don't need to go request a license file. So the barrier to entry is really, really low.
And that was Tim Ansell and Clifford Wolf, both who have been on the show, and we'll link those episodes if people have not heard those. So yeah, okay, cool. Well, that's okay. So I know I keep harping back to this point, but like the reason I ask is because it's like I think about beginners and how confusing it is at the beginning, and I've seen people struggle with Arduino even, and it's like, so it feels like this is another layer of things that need to be done, but I didn't realize that people are still doing the digital logic piece and like mapping that out as well.
Yeah, so if you go to Twitter and if you look at the FPGA Wars hashtag, or if you look at Jesus is another fellow that's working on iStudio, and he's also working on APIO, which is a Python module. I think it's like Platform IO, similar concept for managing building for FPGAs. Basically, you can initiate a project and then you can build it and upload it in just a few really, really easy to use commands. That tool is fantastic. It makes it easy to integrate the iStorm and other open source tool chains into other projects. But Jesus and Obi-Wan, if you look at their tweets as well, and related tweets, you'll see lots and lots of people making projects with FPGAs, for the first time, or posting the results of their tutorial that they passed. One has a huge list of tutorials. They're all in Spanish though, so it's not very accessible for English speakers. But they're working on translating that all to Spanish. And so you can see, some examples, real world examples of people that are using FPGAs for the first time, and they're from that perspective, it's more education, but some people are making some cool projects with it as well.
Okay. Well, what about so I was asking though about the digital, like the schematic drawing level at in an FPGA, right? So they're actually drawing out logic blocks and doing that kind of thing? Yeah. I didn't realize people were still doing that kind of thing. That's the reason I asked. Sorry.
Yeah, and that's a pretty gentle introduction to FPGAs, and then from there they can implement Verilog blocks. So, which I think is kind of a nice next, introduction into FPGAs. If you really want to use the full power of an FPGA, eventually you got to learn Verilog so that you can implement your own hardware blocks.
Right.
You're not going to be implementing a very complicated bit of hardware purely using schematic entry. That's just going to help you understand the concepts and learn the basics. But if you are interested in that and you're motivated, then you'll want to move to more complicated things, including Verilog.
Yeah. And I think, whenever I talk to people at FPGAs, I usually talk about like the streaming nature of data, right? Because I think that making a micro, like a custom micro, is one thing, and that's something you can do. But I think that ultimately adds more levels of complexity. But I think the thing that really starts to open up imaginations and it really even distinguish FPGAs from micros, because I think that's another thing that often doesn't happen as much as it needs to, is just the concurrent nature of it all, right? Like understanding that you don't have to have it in a loop. You can have things where it's just streaming data through is kind of just an easier visualization, for me at least. It goes through these different stages, and at the end, you don't need to, you don't have loops happening, right? You can just have these actions happening, and at the end you have some kind of result. Yeah,
that's a great point. So when you do a digital design, there's kind of two major ways of doing things. One is with a pipeline, a data pipeline, where you can keep streaming data through that pipeline, whether it's doing data processing on it, DSP operations, or implementing an I/O protocol, or all of them. You could combine them all together in one big long pipeline. And the other side of that is doing control. So
like state machines, stuff like that?
Yeah. Typically, you also need to have some control over your design and be able to tell it, when to do certain things, when to stop, what to do next, and in some sort of exceptional scenario. And control is more difficult to implement in digital logic itself.
Right. But that's also more akin to like an if statement in a microcontroller, right?
Exactly. Yeah. Exactly. And so in cases where the control is non-trivial, if the timing required of the control is not too tight, that's why I recommend using a microcontroller in the design or paired with the FPGA, because it is a lot faster to write imperative code in C or C++ or your favorite language. It's a lot faster to write that kind of control logic in there than it is to implement it on the FPGA.
Oh, and so that's why you're saying to combine the two and build a soft micro into the FPGA?
Exactly.
Okay.
So then you can take the complicated control, put that on the microcontroller. It's faster to compile and to reload that than it is to synthesize the design. And then the hardware or the part of your problem that requires either ultra low latency, or it requires extremely high processing speed, or very low power, or some other metric that FPGAs are good at, you implement that in digital logic, and you provide an interface to the microcontroller to control it.
Yeah, could you give us an example of that, like a tangible example?
A serial port. Let's say a serial port that talks to a sensor peripheral, GPS maybe, or some other type of sensor. And then if you have a lot of sensors, you could create autonomous hardware agents that will automatically read from the serial peripheral. It'll perform DMA from the serial peripheral into either system memory of your microcontroller or into a register.
Okay, so is that like you'd read the GPS data sheet, and then you'd say read register 1, read register 2, do this thing, pull the data back, and then put it in this location? Is that the idea?
Sure, you could do that. You could. That's one example. I don't think that's a very convincing example. I have a better example.
Okay, great.
If you have a low power FPGA, like the ICE40 series from Lattice, they can go to very, very low powers with very low power consumption. And let's say you have an Internet of Things node, and it's connected over Wi-Fi or LTE or some other radio, maybe LoRa. And the purpose of this node is to gather data, like many other IoT nodes. So it's going to wake up periodically, collect data, and transmit it over its wireless interface. If you have a low power FPGA, that FPGA itself can be collecting the data on behalf of your high power micro and radio. And so that FPGA could be collecting 15 minutes or an hour of data in a very low power mode.
Okay.
And then wake up the microcontroller and the high power radio every hour or so to actually upload that data.
Okay. And so how would the low power FPGA actually be collecting that data?
So it would have its own digital logic implemented inside that polls the sensor periodically and saves the data that it reads into an internal memory. And when that buffer gets full, it wakes up the larger micro and the radio, and then the larger micro can pull that data out of the FPGA and transmit it over its radio.
Okay. And so I guess the thing I'm trying to get at is in this scenario, does the FPGA have another micro inside of it or no?
Not necessarily.
Okay.
In this scenario, you would want the FPGA to have as little logic in it as possible, and as slow of a clock as possible.
Interesting. Okay.
Yeah, if you do that, then you can reduce the dynamic power consumption significantly.
Okay. And so you're saying that, like a temperature sensor, let's say like a really dead simple temperature sensor, maybe it's I2C based, the FPGA knows to wake up whenever it turns down, it even turns down like the I2C clocking and that kind of thing as well, and then sends some sequence of read commands, pulls the data back, stores it, goes to sleep. That's the idea? That's all it has to do?
Yeah, exactly.
Wow. Okay. That's great. What would it take to actually go and write something like that? That's all Verilog at that point?
Yeah, that would be all Verilog, and you could implement that with a state machine. And so for control logic, if you're not familiar with a state machine, it's kind of, you can kind of think of it like a flowchart. And there's a lot of well-defined patterns for implementing that in Verilog. Something that I would like to do, though, and I don't have the time for it, but it's something that keeps coming back to me. A lot of these types of cases where you want to be able to take advantage of FPGAs, but you don't know Verilog, or wrapping your mind around it is very difficult, because it's a very different way of writing a code, because you're not writing a program anymore. You're describing how to wire up some hardware, right?
Yeah, right.
So something that I've always wanted to be able to do or to see is a really simple way to let people write imperative code and just let it synthesize to the FPGA. And I'm not talking about, complicated high-level synthesis where you're going to get the maximum performance and everything. I want something really simple where I can write a function, a control function, and it gets converted into a state machine that can then run on the FPGA. And then I can interact with that state machine from a microcontroller running on the FPGA. If I can have something as simple as that, even though I'm not getting the full performance, that could enable somebody who only knows C and only, works with Arduino. That would help them pick up an FPGA much, much easier and write, a few different parallel processes, on a whim. So let's say you need another thread to do some pretty simple thing. You can just write another thread that does that, and that can get compiled into a state machine and implemented in Verilog on the FPGA.
Isn't that, I remember, okay, so my FPGA experience is probably from like 2005, so you'll have to excuse me. But I remember there was a C to H function where it was like you had a micro on board, you had written some code for it, you highlight that code, and you say make it a hardware function. I think this was in Xilinx FPGAs.
Yeah, and Xilinx has a lot of high-level synthesis tools for doing exactly that today in Vivado. Okay. And it's much better than it ever has been. But I want... And there's been a lot of different high-level synthesis tools throughout the ages. I don't even want something as capable as that. And I don't necessarily think that we need something as capable as that. If you have the really, really capable high-level synthesis, there's a lot of sort of complicated rules on what you can and can't do because you're writing in C code. And getting good results can be kind of difficult because, C and C++ are unconstrained and they kind of let you do everything.
Yeah, right.
So taking that and converting that into logic is hard to do. I want something even simpler and more limited and constrained in scope. Just so that, you could implement something that works. And then later on you could come back and either re-implement it in Verilog or, use Verilog-like concepts to change the implementation to something more performant.
Yeah. I always liked that idea. That always helped me to understand FPGAs a little bit more, even though I don't think it's actually an easy concept still. But like thinking about like, okay, so you're writing in C, you write some math function, right? Like x divided by y plus some constant that's stored in memory. And it's like you're going to be doing that over and over and over again. And like usually in C, you push that to your ALU and it's doing all the math functions, all that other stuff. But I always thought the C to H function was basically like an escape hatch. It sees that it sees that function is happening yet another time. It has a little escape hatch. It dumps the data down into this trapdoor, and then just an answer comes back up. Yeah. That's kind of how I visualized it. Does that sound right or no?
Yeah, no, I think that's pretty accurate. Because for the most part, especially for control logic, which is significant, most of your stuff is fine running on a slower microcontroller. Mm-hmm. Right? So, and every little bit of control logic that you add, if you're implementing that as logic, like actual hardware logic, every bit that you add consumes more resources. And the resources on the FPGA are much more expensive than bits in a SPI flash or SD card. Mm-hmm. And so the more that you can put on the SPI flash as instructions, the better you can utilize the FPGA for the stuff that really counts, which is the high performance stuff, which could be pipelines or state machines that require extremely low latency.
Yeah. Well, that's an interesting point about resources and cost and stuff like that too, because I saw a presentation at one point, it might have been at a Hackaday thing, but there was someone talking about like the ping-ponging of like parallelization of processes and how FPGAs rose in the 80s and 90s, and then it kind of went back to like, oh no, micros are the big thing, and now it's back to the it goes back and forth based on technology nodes. Micros are pretty cheap. Like, so what is your response to just like, well, I could just throw another M0 at this or whatever? Why is FPGA needed in the world of cheap micros?
I mean, if a micro does the job, then that's what you should use, right? You shouldn't, unless it's for education or because you want to expand in the future or something else. But if you have a very cost-constrained project, which many projects are, you don't want to be spending money on things that you don't need, and a micro does the job, then that's what you should use. There's lots of fantastic micros out there.
Yeah, that the amazing $1 microcontroller, one of my favorite articles of this year. So yeah, I'll do a callback to that.
Yeah. In fact, I have a tiny little programmer board that I developed for the A-series FPGA boards. The A-series don't have built-in USB. Yeah. And I kind of wanted to be able to use an FPGA for that because I have my own USB bootloader. But it turned out that, it would be far more complicated and more expensive to do that. So instead, I have this PIC microcontroller, which the only external devices that it needs is a 3.3 volt regulator and a couple of decoupling capacitors. And that's it. And it can work on USB and, implement my firmware for programming over JTAG. Nice. And that was the right choice because, that micro had everything integrated. So that's a big difference between FPGAs and micros. And it's something that I wish the smaller FPGAs had more of. I kind of wish they had more integrated voltage regulators and clocks that are more accurate. So the PIC microcontroller, you need a certain amount of accuracy for USB. And so this particular PIC microcontroller can adjust its clock based on the synchronization packets coming over the USB wires.
Oh, nice.
And so it actually will adjust its clock on the fly as it's operating in order to do that. But in FPGAs, at least all the ones that I've used, you don't have a fine enough adjustment of the clock to be able to do something like that. So you have to have an external clock.
I mean, I think that's also kind of a... So like in my mind, FPGAs versus micros, like the micros started effectively with FPGAs. It either started in the designer's minds or they started on a board as an FPGA but eventually they just kept getting optimized for their situation, and then people kind of pull them off the shelf and say, oh, well, this will probably work for mine too. So what I'm trying to get at though is like when should people think? I mean, obviously, we talked at the beginning too. It's like yes, it's okay to start at the beginning with an FPGA as well, but in the world of cheap micros, where does an FPGA stand out as a situation? Like especially because our listening audience probably already uses micros. When should they think about switching to FPGA with the tiny FPGA?
So things that FPGAs are fantastic at. One is being able to customize. Let's say you are using a micro, you can customize exactly the peripherals that you want to use. That's one thing that's nice. Two, you can be sure of all of the hardware that you put into it because you can see the actual, because you can see the actual source code for that hardware if it's open source. If it's not open source, you'll have a hard time getting that into your FPGA.
Like one of the industrial ones, EtherCAT.
FPGAs allow you to
like all those,
have room for change in the future. So if you think a protocol might change in the future, let's say you're developing a product, a commercial product, and you need to interface over a protocol like CAN or I don't know, just some other kind of industry-specific protocol. Yeah. There's so many protocols out there, and then there's also vendor-specific protocols. And if you want, you could get a micro for many of those. But if you want to have some future-proof in your hardware design, and you want to be able to get ahead of the competition and support those protocols the second they come out or the second that they're specified, you could put down an FPGA, and then that FPGA can implement that protocol for you. And it can implement, future protocols, provided that they are electrically compatible. Or if you use something like FMC or some other expansion header, you can implement other protocols even if they're not electrically compatible. Let's say you need to use a PHY layer in between, or some passives, or something else to do the actual interfacing. If you have that interchangeable hardware end, then you can do that as well. So then your main board can stay, fairly similar or the same over time. And you can change the design that's implemented inside to account for either bugs or new features or new capabilities and new protocols. And then if really needed, you can exchange the kind of like the hardware front end for the electricals to change out the PHY or connectors. And so it gives you a lot of flexibility in the future.
It's almost like a business case too. Like you like keep selling the same hardware for a long time as well.
Yeah.
Like what's the one? So I have I got for work. I got a video recorder. It's like a external recorder for camera outputs, and they sold upgrades even for it, where it's like you want like a instead of having just 2 recorded streams, you could then do 4. You could then do faster bit rates when they verified timing and everything. Nothing changed other than basically the bit stream that it just looked like a firmware update. But you could tell that there was obviously a bit stream that went down into the actual device as well, and so
yeah. Another case where FPGAs are very useful is in test jigs, where you need to test your own hardware, and you need to emulate the devices that your hardware might be connecting to. With an FPGA, you have full control, so you can perform the exact scenarios that you want, and you can do it, pretty much as fast as you want to do it, depending on how your hardware supports it.
So this would be like if I was making a board that was plugging into the rest of my system. You're saying that I could like emulate the cable plugging in what the cable it's plugging into, and then like simulate signals that might be coming over that cable. Is that the idea?
From a logical connection perspective, yes. But if you're talking about, sort of the analog characteristics of having a long cable, obviously you would need. No,
sorry, I just meant the digital. Yeah. So if I'm plugging, if I have a processing board and then I have a sensor board, and the sensor board's sending back SPI signals, but it's a volcano monitor or something crazy like that. I don't have a volcano to monitor, but I need to still send back some crazy temperatures that I might have a stored file for. You're saying the FPGA could actually send those numbers back.
Oh yeah, and an FPGA could really control the whole process, right?
Yeah. Okay.
And so your entire and this would be like manufacturing testing, right? Your entire test suite could live there. I've had people buy I had somebody buy a series board, 2 A series boards, and 2 programmers. And these are like really cheap parts. One's $9 for the programmer, and I think he got the $18 A series board. And he had them overnighted with FedEx first thing in the morning across the country. And it was to 2 different locations. So it was like $150 or $200 of shipping for a few dollars of FPGA parts. And the reason why is because this person was using the same FPGA in a product that he was developing, and he was having some issues with his board and with the programmers that he was using. So he wanted to isolate the problem and try out the Verilog on the tiny FPGA board, which only has the FPGA and the absolute bare minimum of passives for that FPGA to function reliably. And so there's a lot of use cases for these things. It's not just hobbyists and makers that are buying the tiny FPGA boards. It is professionals that are using them as well.
Well, let's walk through some of these some of the hardware. So you said A series, and I believe I saw B series as well. So what is the genesis of, like, where did this all start, and then what is the hardware today?
Okay. So it started a little bit more.
Here we go.
Yeah.
Here we go.
This is a little story. So it started a little bit more than a year ago, and I love FPGAs, and I've collected multiple FPGA boards and done pretty small projects with them, just kind of messing around. And I really like this tiny form factor. Like, I'm infatuated with it. I don't completely understand why, but I love the fact that I can have so much power and capability in such a small module.
And how big are we talking here?
The A series is 1.2 inches by 0.7 inches. And the B series is 1.4 by 0.7. So the B series is about the size of an Andes Mint.
Andes Mint. Okay.
Yeah, those.
And you had said before the show, before we started recording too, it was similar to the Teensy size.
Yeah, right? It's the exact same size. It's the same form factor.
Same size, but not the same pinout, right?
The pinout for power and signals, I've kept compatible for power and ground. Sorry, so that you could, if there's a breakout board for a Teensy, you should be able to plug in a tiny FPGA board for the most part. There's some signals that...
Oh, interesting.
Yeah,
okay.
There's some signals that the Teensies have that I don't have.
Yeah.
There's
like DACs on
exactly.
board, right?
And so I haven't replicated those. And then there's other signals with headers that are in inconvenient locations that I didn't break out.
Yeah, I was wondering because you have the... well, I was also wondering because I just did something stupid last night. And I was playing around with actually soldering these down directly to a board, and it worked. I'll share that tweet. I soldered a Teensy directly to a footprint that I created. But I was wondering if it was the exact same thing because it looked like the internal surface mount 0.1 inch headers were also the same on your board.
They are very, very similar. The difference that I made, number one, is the analog signals. But number two, I added 2 extra ground pins. And so at the bottom of the Teensy 3.2, there is a row of 5 through holes for a header. I don't have that on my board. I didn't have space.
Yeah.
And so instead
I'm actually okay with that. I think that's kind of that's where the DAC is as well.
Yeah.
And I'm not a huge fan of that because then you can't necessarily plug it into a breadboard because then that line goes across and they're...
Yeah, if you use that, it makes it a little bit harder. But I think the use case, and I think one of those pins might even be like a higher power pin, or maybe that's just the teensy low cost. But you can drive LEDs and stuff off of that, or those long programmable LED strings.
Yeah, the WS2812s.
Yeah, so instead of using that, I added 2 extra grounds, which are really important for sort of high speed signaling on FPGAs.
Do you have people that are using it like that? The FPGA?
With the headers on the bottom?
Like plugging into Teensy boards. That's what I mean. Sorry.
Not yet. I haven't seen anybody do that yet. But somebody did create a breakout for the BX board. I think talldog.com. I have them somewhere. He does breakout boards for the Teensies, and then he saw the Tiny FPGA BX crowd supply campaign, and he just emailed me out of the blue with his breakout board design, and I'm like, oh, awesome! This is one less thing that I have to do. Thank you.
Yeah. Yep, I found it here. Okay, so it's just a way to get kind of a wider form factor, it looks like.
You can break out all the pins on the bottom.
Pins. Oh, the stuff on the bottom too, I see. Okay.
And the way that he made these boards is really cool because he found these tiny pogo pins for the test points. And so he has this footprint that allows you to manually solder those little pogo pins on the breakout board. And then when you put the FPGA board on top and you solder it in, all the test points make contact with those pogo pins, so you can even break out the test points.
Wow, that's great. Yeah, it's nice. And that's usually just used in your programming side of things, is that right?
Yeah. So I have a test jig that uses those test points for testing out connectivity to everything, as well as the voltage levels, and there's a reset signal for the FPGA. So when I program the SPI flash, I have to keep the FPGA in reset so it's not conflicting with the SPI bus.
Okay, so between the A and... So what is the difference between the A and the B series?
So the A series was the first board that I made, and it's very simple. I basically went... I was looking... Originally, I was looking for another FPGA board, the Bugblat TIFF. So that's Bugblat, Bugblat, TIFF, TIF. And that was an even smaller board, and it was powered by a Mach XO2 FPGA, and it had a USB interface chip on it, and it was really bare bones. But it was awesome because it was the smallest FPGA board, that I could practically use, that I could find. And so I had bought a few of them. Yeah. And then I wanted to buy more about a year ago. And the guy that made them said, well, the yield on these boards was low because of the BGA package, so I'm only going to make them if you want to order a whole bunch, like for education or something like that. And I wasn't really willing to do that because that was getting very expensive fast. So I thought, well, here's an opening. I would like to make this. And so if this guy can make it and other people can make these boards, then I should be able to do the same thing. And so I went looking for FPGA packages that would be easy to use. And there's not really. there's
you noticed that, huh?
Yeah, there's very few. There's some that are easy to use in like TQFP or the quad flat packages.
Like the really, really big, like the 208 pin flat packs, right?
Yeah, which totally blows out the form factor. So I couldn't use those.
Yes, it does. Right. I mean, what's crazy too is like you look internally, you're like, oh my God, it's just like, it's a 0.5 millimeter square of silicon, it's like
yeah. And so then I looked at the QFN packages. I found those from Lattice. The Mach XO2 packages, or the Mach XO2 FPGAs have QFN. And I thought, well, I should be able to do that. I saw a soldering tutorial on how to solder QFN 32. I might be able to...
What could possibly go wrong?
Yeah, what could go wrong? So I actually ordered some breakout boards from Adafruit, QFN 32 breakout boards, which are nice. And then I just proceeded to destroy them, trying to solder chips on because I'm not really... I wasn't really that great at soldering in the first place, and QFN is not... It is not easy to solder that. It is very difficult. So I quickly learned that the way to do that would be with a solder paste stencil and... using a skillet.
Yes. And also we didn't really talk about it, but you are mostly, most of your days, you're a software person, right? I mean, you have a hardware background, but you are software most days. So not hands-on soldering most days. That's what I'm trying to say.
Yeah. Especially when I started, I've gotten significantly better. Now I'm pretty happy with my soldering skills between through-hole and, hand soldering surface mount. But for surface mount, I almost exclusively use solder paste and stencils and reflow. It's we advise people do the same here at the Amp Hour, so that's good. Yep. So
cool. Okay.
So I ended up designing a board with just a very simple board to kind of get my my feet wet and try it out. And I send it off to... I look for some manufacturers, so I send it off to PCBWay. And then I look at the quote, and I'm like, gosh, there's not a big price difference between like 10 and 250. I might as well make 250.
Yeah, why not? Right.
And then I got some prototype boards back, and I reflowed them on a skillet, and I had some low temperature solder paste, which was nice and forgiving and easy to use for the prototypes. And I had like a $20 skillet that I used, and I just turned it up. Yep. And then once it starts getting shiny and smelly, I decided, well, that looks like good, and I turned it off. And I was lucky; it was good enough. So I had my first 25 prototypes.
And this is the tiny FPGA A1, right?
Yeah, it's the A1. So I thought, well,
yeah, there's not much on these boards at all. I mean, there's it's a micro or a FPGA and a bunch of caps.
Yeah, it's a bunch of caps. It's some pull-ups or pull-downs. I had a ferrite bead in there, and have some bulk capacitance. And for the next gen, I added some LEDs because people wanted a power light and they wanted a user LED. Yeah. And I used way too low of a resistance value, and so the power LED is blinding. And what I've done on all the AX1s, not the X1s. Yeah, the X1s, I've had a black permanent marker, and I just dabbed the power LED with a black permanent marker, so that people aren't blinding themselves while they try to look at their user LED, which is blinking.
That's a good bodge. I like it.
Yeah. So now I use 10K resistors on the LEDs because it's plenty bright, and they're just for indicating that, you don't need it to light up the room.
So those were both XO2. I actually don't know this family. Sorry. So it's a Lattice.
Yeah, Lattice Mach
family?
XO2, and those are kind of like a CPLD replacement. So they kind of fit where CPLDs would have fit, and they use a FPGA fabric with LUT4s and routing matrix with some distributed RAM. No DSP blocks. But besides that, they're pretty nice for doing embedded things and connecting up different IOs.
Is it large enough to put a micro into those?
You might be able to put a really small micro.
Okay. Yeah, because I'm looking at your comparison sheet here. It looks like your board, the A1, has 256 logic cells, 2K bits of distributed RAM.
Yeah.
21 user I/O pins. So that looks like a CPLD to me.
Yeah.
And then the A2 has 1200 logic cells, 10K of RAM, 64K block RAM, and then some flash as well. So that looks a little bit more like you could fit a micro in there, but yeah. Tiny.
I think a better use case would be to use it in conjunction with a separate micro.
Got it.
The Mach XO2 has some nice integrated peripherals, like a SPI peripheral. And so that would be a great way, reuse that SPI peripheral in your FPGA and connect it to whatever hardware you have, and then use a microcontroller external to control the FPGA over SPI.
Got it. Okay. And you're saying that's a hard SPI block?
Yeah.
Got it. Okay. Cool. That's good. Okay, so then what made you move to the BX? Why didn't you call it the B1?
Oh, yeah. So from the beginning, I wanted to have USB. And so I looked up the cost of the FTDI chips, which everybody uses, and almost everybody, and because it's compatible with the software. And I just was shocked that they're like...
Yeah, $5, right?
And for the Mach XO2 FPGAs, I'm like, that's, twice the cost of the FPGA. That's crazy. Yep. Like, why would I get that and not a more expensive FPGA? And of course, the reason why is because you still need a USB interface. And so
you pay now or you pay later, right?
So the A series boards, I wanted to learn how this stuff works, and originally I wasn't going to manufacture it and sell it. This was mostly an exercise for myself, but then gosh, it's so cheap to have just a few assembled. I might as well have 250 assembled. So I did that, and I put a store up on Tindy, and then I thought, okay, I really want to make an FPGA board that has integrated USB, and I think I can do it without an external chip.
Remind me, do most micro dev boards have integrated USB or no?
The good ones do.
Okay. And say the good ones, like expensive ones? Or?
I think micro boards for that are easy to use. It's fantastic to have USB on it.
No doubt about that. Let's just use Digilent as an example. We've had Clint Cole on the show before, and I like Digilent makes a lot of low-ish cost, FPGAs. They do some big stuff, but like, do they put FPGA or USBs on the board?
Oh, you mean for FPGAs? Yeah, almost every Digilent board that I've seen has USB over FTDI.
Okay, so it's not. I'm just wondering, is it a non-standard thing these days? But it seems like most boards will have it these days instead of using like a JTAG program.
Yeah, most boards will have it, and I think it's really important to have that if you're trying to appeal to, makers and hobbyists, because they're used to having that USB capability and not having to use a separate programmer. And if you can just plug it in over USB, it's so much simpler, and it lowers the barrier to entry. If people see that you have to also buy this separate USB programmer or FTDI programmer, and they see what it costs, that's just going to put them off to the whole prospect of trying it out.
Yep. Yeah, no, I think you're right. And I think at a certain point, the benefit of a dev platform in the first place is it's just like, well, I might as well try it. Like $30, who cares, right? It's
exactly.
Like, it's worth just getting one and seeing how it goes.
Exactly.
Or in the case of like, when I shop at Oshpark, I'm like, yeah, Teensy, $15 in there, or $18, whatever it is. Yeah, throw it in.
Yeah.
It's like, yeah, that's great. I actually really like that. I think that enables weird, having boards on the shelf can actually really enable you in the future.
Yeah.
So
So
mindless purchases, folks. That's what we're promoting here at the Amp Hour. Mindless purchasing.
Yeah. And that's actually a use case for the small FPGA boards as well. You need something implemented in Digital Logic or something quick. You don't have the parts on hand. You can use an FPGA board to do that. Yeah.
I think having something like these tiny FPGA boards on your shelf could get you out of a couple of binds. Yeah. Like you were saying with test jigs or just micro or just regular projects, I think that, you could spin something up pretty last minute.
Yeah.
Hackathons.
Oh yeah. Yeah. So for the B series, I wanted, all my boards, I figured I would like to be able to offer multiple sizes, at different cost levels, at different price points, because I really wanted, if somebody can't afford the more expensive one, I wanted them to be able to get the less expensive one, at least to have that option. And so for the B series boards, originally it was going to be B1 and B2, because I had identified this chip I could use with the same package, same footprint, and it would work, with different capacities. Well, the lower capacity one was hardly any cheaper than the higher capacity one, so it wasn't really worthwhile to have two different products. And so that's why you saw, originally I just had the B2 out, and there's no B1. It doesn't make sense. It'd be like $3 cheaper. So nobody would really buy it.
Oh, you did have a B1. Oh, I didn't realize that. I'm sorry. I was just making a joke about that.
Well,
so there was a B2 board.
Yeah, so my original B series was the B2 board, and it was called the B2 because I actually was planning on having a B1. But the B1 would have cost $35 instead of $38. And so it wasn't really compelling for anybody to buy that one versus the bigger one. And for the B2 board, that was a slightly different design, and it sold all 250 of them, and then they ran out of stock. And so then I was trying to figure out, okay, I need to do another manufacturing run, but there was a few things that bothered me about the B2. There weren't enough pins. I used a 2-layer board, which means that my ground plane on the bottom was like, Swiss cheese.
Swiss cheese.
Yeah, there was cuts in it all over the place, and I wasn't.
I have a complaint about your board, which you actually did not rectify, and I wonder how it goes.
Well, okay, I want to hear it.
Surface mount USB connectors, not even once. I don't mess with those. Why? How many people have been like, "Hey, I ripped the FPGA or the USB connector off"? Has there been a lot of that?
So far, zero. But there's only 250 of the boards of the B2 boards in people's hands. So that could change over time.
Got it.
But yeah.
I would just like to state unequivocally, I always try and put through holes with a USB connector because I've ripped so many off of boards.
Yeah.
Even super glue doesn't help.
Yeah, and I think if I'm using the USB micro connector again and I'm doing another design, I'll probably move to a USB connector that has the through holes on the sides on the shield.
Yeah, exactly. Yep.
Yeah.
Just to get that lock from that. Yeah. You could still rip them off. I mean, a dedicated person such as myself has ripped off every type of USB. Yeah. Okay, so you moved to a 4-layer though. That's
Yes.
good. And yeah, I'm looking at I think a picture of it. I think this is different because I don't see as many cutouts on the top side.
Yeah, so I moved to a 4-layer, and then I committed some different. So I committed some BGA sins on the first one, and for this one I committed some different BGA footprint sins.
Okay. What is the BGA footprint? So this is the ICE 40.
Yeah, so this is the ICE 40 part. It's a 81 ball BGA with 0.4 millimeter pitch.
Ooh, boy. Okay.
And this is
your first design.
This
too?
is my first BGA design. Yeah.
Whew. Yeah, we were talking about that on the show the other week. I have still not done one, surprisingly, and I was also thinking about doing this, and Dave talked me out of it. So, how'd it go?
Not as bad as I thought it would be. So this package is absolutely not meant to be used on a normal PCB process. This package is meant to be used on a HDI, high density interconnect process where you have either via to route out everything. I think the official recommendation is to use via in-pad with, 0.2 millimeter vias and like a 0.1 millimeter drill. And then you have to fill and plate the via hole.
Oh, like plug the vias.
Yeah. And that's expensive. That's very expensive. And that was not an option because just to get prototypes for that, it would have cost, thousands of dollars. And so I couldn't do that. But this is the only package in this capacity that would fit the form factor. So I had to use it. And on the B2, I had already done it on the B2. But one of my complaints with the B2 is I didn't have enough IOs. And so on the B2, what I did is because it's an FPGA, the IOs are very flexible. And most of the pins on that particular package are the IOs. And so for really important things like the SPI interface, which is how you program the FPGA, they were kind of a little bit deeper in the footprint. And so what I did is I just routed over other pads. And if you don't use
over other, you just didn't. So you basically covered up those pads with solder mask.
No, I routed over those. I routed over other I/O pads that I wasn't going to be using, that I was kind of sacrificing. They're not covered by solder mask. The pad is still there. It's just that in the schematic.
Oh, so you're just like driving a tri-stated pin at that point.
Exactly.
Is that the idea? Wow. Okay, that's interesting.
And so on an FPGA, if you don't use a pin, one of the I/O pins, in almost all cases, it'll be tri-stated by default. So the driver's disconnected. It's not going to be doing anything. And so it's safe to do that, as long as your users don't try and drive that. And most people don't try to do that because the only way you would know
if you
that
tell
pin
them very explicitly.
And I provide pin constraints. So I provide a pin constraint file that shows the mapping of the pins to the pins on the board itself, and then I provide a template that has a top module that has all of those pins listed, so you can use them very, very easily.
Yeah, I'm guessing your users really want to. So, like, if I'm looking at the BX board right now, and you have G and then 1 through 13 on the left side and 14 through 24 on the right side, and like I'm guessing that your users want to be like pin 24.
Exactly.
Right. Yeah.
Exactly, and that's way more convenient than trying to mess with the pin constraints themselves.
I mean, yeah, if you don't have something like that, then the user has to create it, and it just gets created over and over again. So as long as they're, I think if they're using a board like this, and then they decide, no, I want to put an ICE 40 81 pin crazy BGA on my part, then you have to go and redo it. And it's like, that is the time to go do it, I think, too.
Yeah. So on the B2 board, I was able to route over both power and signals and important control signals by kind of connecting them to the pads and then routing them all out. I had considered using solder paste, the solder mask to block some of the pads, but I rejected that idea because I was too worried about it messing with the BGA reflow process.
Right. Yeah. It could. I mean, like you can't really count on solder mask to completely insulate.
Exactly.
So you could have weird intermittent problems too.
And then for some ground pins and power pins, I also had to. And even for some signal pins, I did this so I could route out some more signals. I used a via, and I would gang together 4 pads, and I would put the via in the middle of those 4 pads.
Right.
And it's a pretty big via, but there's solder mask. There's plenty of solder mask between the pad and the hole in the via. And the via annular ring is touching all the pads.
Oh, really?
Oh yeah.
Wow.
It's not cleanly fitting in there. I had no choice but to take 2x2 quads of pads and put a via in the middle of them.
And so what is the constraint on your PCB process? What's the process you're using?
So I'm using PCBWay, and they can get down to 4 mil traces in spacing. And then the vias can go down to 2 millimeter drills with a overall diameter of 0.5 millimeter. And that's kind of their standard.
Is it 0.2 millimeter drills?
Yeah.
You said 2 millimeter.
Sorry. That would be way
big.
Too big. Yes, 0.2 millimeter drills.
I was just gotta, I'm a little metric challenged myself, so gotta double check.
Well, PCB layout doesn't even help that much because it's split between metric and imperial.
I didn't gotta get good at that 25.4 conversion.
Yeah, I figured that one out now. But I didn't even know what a mil was when I started.
Oh wow!
I had seen it on
software into hardware, huh? You are. I'm impressed. I'm always impressed with people with you, like you, who just go for it. It's awesome.
I had a lot of fun doing it. That helped.
That's
that
good.
motivation really helped.
That's good.
So I was able to escape a bunch of I/O for the board and the power, and it worked actually, which kind of blew my mind. I was really. This is the first BGA I had ever done. I was able to assemble some myself. I could hardly believe it. Mm-hmm. But for the BX board, I wanted more IOs. That's something that really bothered me. So what I did to get more IOs out is I took the outer pads of the BGA and I squished them down to 0.1 millimeter, and then I elongated them. So now they're like 0.35 by 0.1 millimeter. So they have about the same surface area, and they're going to be able to grab the balls and be able to wick them on and reflow. And I was able to get a lot more IOs out. I was really happy with it. And so I ordered some.
Are your files online anywhere?
Yeah, everything's open source. So github.com/tiny FPGA, and the BX series.
What is the package type? What do you use to do it?
I use KiCad or KiCad.
Hey! All right. This is the long con. I knew this in the beginning. That's the only reason Luke's allowed on the show. No, I'm kidding. I could actually tell from the beginning because you used the built-in text generator to say BX and B2, and I know that font by sight, which makes me sad. Okay, so that's good though. So, and I mean, people could view the Gerbers either way, right? So
yes, I should have the Gerbers up there. If I don't, I can add them.
Yeah. Okay. But they can also generate them with.
Yeah. So people ask me to upload the Gerbers, and they want to see the PDFs. And I originally had thought, well, anybody can look at it because it's, KiCad, or how do you pronounce it? KiCad or KiCad?
This is a contentious thing.
Gosh,
I say KiCad.
I always say KiCad.
There's actually a Wikipedia article that was recently amended to say KiCad because Wayne, the project leader, says that. But the debate continues.
Okay, so I'll be careful then. So
there's a T-shirt if people are interested. They can pick their side.
That using an open source FPGA or a PCB layout and schematic entry program, I would be safe from having to upload the Gerbers because everybody could download it and everybody could use it. Mm-hmm. But still, people, they don't want to have to do that. So then I relented and uploaded PDFs, and now I need to relent some more and upload Gerbers as well.
Yeah, I mean, there's online viewers you can do too. I'm really waiting for. I think GitHub will eventually do it as hardware hopefully keeps getting more interesting to them. But there are online viewers you could do, so you might want to just upload the Gerbers to that too, and you could just link people to view the Gerbers.
Oh, yeah, not a bad idea. Actually, that gives me a good idea. I could. There should be like a JavaScript plugin somewhere.
Yeah, exactly.
And I could put that on my website.
Yep. That will save you some. I don't want to download this problems.
Yeah. So
okay, so you broke out more pins on the BX though, which is good. So what is the total count on the BX then?
A total of 41 IOs, where 31 of them are dedicated to whatever function you want, and 10 of them are shared between the boot LED or the user LED, and USB and the SPI flash.
So how would that work? Is it like once it's done and programmed, it can like switch modes or what?
On the SPI flash, the easiest way to reuse those pins is if you have another SPI device. And so you can reuse most of the pins and then have a separate chip select.
Okay.
Alternatively, if you're really careful about how you use them, you could share them with a different bus. Or just LEDs. I mean, after boot up, if you don't use the SPI flash, you can reuse most of those pins for other things, as long as they're not conflicting during boot up. Mm-hmm. And then for USB, you can reuse them as long as you don't need the USB interface. It just makes it complicated to use those. That was another thing.
Right, so it's a best case scenario to not use them, but you're saying that you can if you're in a pinch.
Exactly.
So how would it work? So if you were using, so say you put a like an ADC onto the SPI bus as well, right? So that's what the SPI flash is normally pulling from, whatever. Is that just because when the FPGA wakes up, it hits the chip select for the SPI flash, goes and reads what its bit stream, programs itself, and then it says, okay, now I'm an FPGA. I know how to talk to the other chips that are on this bus?
Yeah, exactly. So once the configuration process is complete, all of the SPI IOs on this particular chip are handed over to the user design. And so the user design can do whatever it wants with them.
How do you expect people to be using this mostly in dev projects and like wired together type stuff? Or do you think that people will eventually start kind of doing what you're doing and pulling FPGAs into their PCB designs as well?
That's a good question. I think most of the people that are using it today, with a few exceptions, are using it for their own development projects, right? Mm-hmm. Not necessarily for a new PCB. But I've seen a few people develop their own PCBs using the boards, and I've had a few people ask me, if they use this, would I recommend using the same FPGA? And sure. I would not recommend using the same FPGA package.
Okay. Yep.
Because it's not really meant to be used in this way. And I would recommend a much larger package because it's so much easier to use. Even a larger BGA package, if you go to 0.8 millimeter pitch, it's so much easier.
Yeah.
Like you don't have to do weird things. Right.
You're saying you can escape in the normal method, like on a 4-layer board, no problem.
Yeah. Exactly. Yep. You can use regular sized vias that don't cost crazy amount of money for prototypes.
What about, I was going to ask, again, because I've been playing around with this, have you thought about doing a castellated design for your board?
I have thought about it, but that makes manufacturing a little bit more complicated. So
Really?
I'm not familiar with castellated, so I might not know the ways that people work around this. But if the two edges are castellated, on the front, I also have the USB connector. And so right now on my panel, I route out the top and the bottom of the boards so that the USB connector has space to sit, because the lip of the connector goes over the board a little bit.
Got it.
And then, so I can't connect anything there. Like in the panel, I can't have any tabs there. And then on the sides, if it's castellated edges, I couldn't have any tabs there either.
Yeah, that's true.
So then,
that would leave me the back. Move your USB in, right, or something.
I would have to have a different USB connector, I think. Yeah. And then
you're thinking about doing that anyways, so
Yeah. And then the other reason why I haven't done it when I started out is because I felt that the normal use case will be people wanting to solder pins on or wires. And I thought that if it's a castellated edge, it would be harder for more people to be able to solder the pins on.
Yeah, right. I think this is... So, I mean, I guess that kind of does point back to the thing we talked about at the beginning, was this is meant as a beginner platform trying to get more people into FPGAs as well.
Yeah.
Okay. Okay, so someone listening right now says, I'm going to go buy a BX board. They get it in the mail. They're like, this thing's beautiful. I really enjoy it. What is the next step?
So on my webpage, I have a B series guide, which is kind of like a getting started guide. So this is what you can do to get your development environment up and running, and it leads you through a simple example to get the LED blinking. And then beyond that, there are some resources for learning more Verilog and doing other projects.
Okay.
I need to rewrite that page.
And we should I was going to say, we should clarify, the B2 board is the BX board, right?
So the BX is the next gen of the B2 board. Yeah.
They're functionally equivalent though, or no?
They are not. They use almost all the same components.
I guess maybe the edge connector pins are all the same.
The footprint is different. You'd want to use a different pin constraint file.
Okay.
Yeah, but I take care of that for you basically. So there's templates that you can use that kind of abstracts that away.
Cool. And then so people using this, they would be doing this from the command line using the Ice Storm project. Is that right?
You could do that. Unless you're already really comfortable using Ice Storm, I don't recommend that. I recommend instead using either APIO on the command line, which allows you to do things like APIO init, which will initialize a project, and then APIO build, and then APIO upload. And that's it. It'll automatically know how to build the whole project based on the top file, and then it knows how to upload it to your FPGA board. So if you want to use the command line, that's what I would recommend. But if you want an IDE, I recommend using Atom with the APIO IDE plugin.
Okay.
And I'm actually going to be rewriting my B series guide to use that instead, because that's all open source and it's super easy to install and use.
So I was going to say, I'm looking at this right now. It's using the actual Lattice toolchain in your existing B2 guide, right? Yeah,
and IceCube 2 is like what Lattice had out for the Ice 40 FPGAs. It's not really that great to develop in.
To me, it looks like traditional FPGA toolchains type stuff. It's a little bit simpler, but yeah.
It's way simpler. It's uncomfortable to use. Atom IDE is way better, and with the plugin, it's much simpler.
So, so I'm looking at the IceCube UI here too, and it does talk about place and route and all that stuff. Synthesis, place and route. Actual programming. How much is visible if people are using an APIO thing? How much is visible to the user then? Like, how much do they need to know about timing constraints and pin files and all that other stuff?
If you're using APIO, you still need the pin constraint file.
Sure. I meant more like the knowledge of it, though, right?
So but the knowledge, you wouldn't really need it unless you're really trying to push the design into high performance.
Yeah. No. I'm really talking about the blinky side of things, right? Because honestly, that's the hardest thing. Is that I think if you go download, I don't remember what Altera calls it anymore, but the Altera tools or the Xilinx tools, they're like, this is your control panel for doing everything. You can tweak every knob. You can make it completely custom. It's like, that's great for a 20-year FPGA designer. For a beginner, it's like your jaw drops and your stomach drops, and then and then your motivation drops. Most importantly, it's like that's really tough.
Yeah, it's super intimidating, and it puts a lot of people off. When I was talking to people at Maker Faire, that was the number one thing that people had worked in FPGAs before.
Yep,
it was several years ago, and they were totally put off by the tools.
Yep.
So there's a lot of
there's a lot
of work.
Matters. And as a callback to the Arduino folks, whatever people think about the hardware, I think it's the simplicity of the programming interface that really matters. And that's also what I like about the new micro/circuit Python stuff too, right? It's just, it really matters to get people into it, and having tools that are enabling that is really important. So if you think, if APIO is that, I think that's almost like, in the past I have pushed back and been like, oh, that's kid stuff, right? But I have revised that stance many times over, because I've run into, every time there's a new platform, you got to learn the new thing. So
yeah, and
it's better to have something simple. Yeah, exactly. And it's better to learn something simple and get some of that dopamine, that sweet, sweet dopamine, and then move on from there.
Oh yeah, I agree.
How far can people go with an APIO? I mean, type of situation.
So with APIO, you can, if you want, you can add constraints, but I'm not sure. Right now, the Ice Storm tools don't support most constraints. I think they only support pin constraints. I'm sure somebody will yell at me later and say I'm forgetting about something. But there's not a lot of like stuff that you'll be able to do there. But you can do. I mean, APIO itself isn't going to be restricting you from doing much of anything.
Well, I guess it's more about how much visibility it has to like under the hood, right?
And on Ice Studio, there's not a whole lot of. I'm sorry, in Ice Storm, there's not a whole lot of knobs to tune at this point.
Okay.
But going forward,
but that could be a blessing too, right? I mean, like that's nice.
For new users, it's fantastic.
And so when they move forward, then they'd have to move into using like an Ice Cube or the more traditional toolchain type stuff.
So the SymbiFlow guys are making a lot of progress. And so SymbiFlow is like the next generation of the open source FPGA tools. And Tim is very close to having a bitstream, and maybe he might have done this already, but he's very close to having a bitstream being output from SymbiFlow for Ice40.
Nice.
And so SymbiFlow has a much better place and route backend, which is like one of the really complicated parts of doing the bitstream generation. And that
I actually did not even know that SymbiFlow is one of Tim's many projects, as he talks about.
He does a lot. He does a lot.
He does a lot. Yes. Anyways, sorry. So it's on the cusp, though. You're saying.
Yeah, it's on the cusp, and SymbiFlow will support the 7 series FPGAs from Xilinx. There's work being done on that. Dave Shaw is FPGA Dave on Twitter. I'm getting tweets and commit messages, all hours of the day, with his progress of documenting the ECP5 FPGA. ECP5 is a larger FPGA from Lattice that I'm using in my next tiny FPGA board, the EX.
Cool.
So that's really exciting.
When's that coming out?
So I had some prototypes built of the EX a while back, and it took a really long time to get them because the ECP5 package, the specific package I'm using, is kind of hard to get.
Okay.
But I want to redesign it because I actually want to use the high-speed SerDes on the ECP5, and I want to route them over to a USB-C connector.
I was going to say, what are those and why should people care about them?
So if you use the high-speed SerDes, then you can connect your FPGA board to hopefully USB 3 and or PCI Express. And so if you want to get data in and out of your design very fast, that's the way to do it. And that can connect you up to standard interfaces on computers or embedded SoCs, project boards,
so you're saying doing that instead of having a chip that does USB to serial,
so the benefit of that is these external USB chips are very expensive, and one that can do USB 3 is at least $10.
Wow.
And it has a very specific interface. So there's an open source USB 3 device that I'm working on porting over to ECP5, and then I want to port the PHY layer to work on the transceivers that are in the ECP5 itself.
Nice.
Yeah.
That'd be great, yeah.
Super excited. I'm looking at a 3D model of the redesign right now. And I have a USB-C connector, and you'll be happy because it has holes in it for the
tabs.
Yeah, for the shield to be soldered in. It's very solid. And it's going to be an awesome design. It's going to be the smallest. It's smaller than a stick of gum, and it will have USB 3 on it and PCI Express, SD card, DDR, SPI flash, and the FPGA on it. If I do the power delivery network well enough, you could get some. You could get the 85,000 LUT4 part on it. ECP5 is a relatively low power part for the size.
And that would be a 12x improvement, right, on your current size?
Yeah, that would be huge. So I'm not 100% convinced I'll be able to support that full size with like a full power hungry design. But I am pretty convinced that 25K and 45K should be very happy on that board.
And what are you targeting that time frame for?
I would like to have a crowdfunding campaign for it in the fall.
Okay.
So early fall, late summer, and then I want to put that on Crowd Supply as well.
Yeah. Oh, yeah. We should talk about that. So you had the BX on Crowd Supply in the first place. So how did that all go?
It actually was awesome.
You learned 2,332,300% funded.
Yeah. So
because you cheated.
Yeah, I did. I was trying to figure out what's my minimum funding, and then I thought, I didn't have any crowdfunding for the B2 boards, and I made them and I sold them. So I'm going to end up making these boards, I decided, regardless.
Yeah.
And so I put my minimum funding as $1. And the crowdfunding went much better than I expected. And I think most of that is due to actual marketing.
No, don't say it.
Yeah. So I've learned a lot about engineering and PCB development and FPGAs and Verilog and even USB digital design throughout this whole project. But I think I've learned even more about, doing shipping and fulfillment and the business side of things and strategy and marketing and, networking with people. I've learned so much more of these, soft skills and business skills that I had always kind of discounted before. And now I really understand their value so much more than I did before. And it's actually a great perspective
evolution for engineer, huh?
Yeah. Yeah, kind of that.
People don't have to have it, but I think the idea is like if you're kind of doing a side project or you're out on your own, that is kind of the currency that other people work in.
Yeah. And I
was
scared of doing a crowdfunding campaign starting out.
Yeah.
Because I knew I had no experience in doing this. And so I was afraid that, I would get this project funded and then I would ship 1,000 boards out and then I would get 1,000 complaints coming back, for different things not working.
Right.
The B series boards, I implemented a USB device in the FPGA fabric. That's how you program it.
Oh, really? I didn't know that. Okay.
Yeah. And so the ICE40 FPGA has this really nice multi-boot feature. And it's really easy to use. In your SPI flash, you can have multiple configuration images. And then there's this multi-boot primitive that you can instantiate in your design. And you can tell it, which one you want to boot into next. And so once you tell it to boot into that next design, it'll go ahead and do that. Because the FPGA has that capability, I was able to forego having an external USB chip. So when you plug in the B2 or the BX board, that USB connection, that USB device is implemented on the FPGA fabric itself. So that's the default boot. So it boots up, implements the USB device, gets enumerated as a serial port on the computer, just a standard serial port.
Sure. Yep.
And then you can use the programmer tool to download the bitstream. After the bitstream's downloaded, the USB device internally tells the FPGA to reboot. And so it completely wipes out the current design, the bootloader, and it loads in the user design. And so this was for like zero cost. I could implement a USB interface. And this means that the boards are probably $20 cheaper for the user to buy than they would have been otherwise.
The bootloader's still stored in the SPI flash though, right? So if you needed to do a hard reset, you could still bring it up.
Yeah, so every time if you boot up and you're plugged into a computer, into a USB host, it'll load the bootloader and it'll stay in the bootloader. So it's ready for you to either tell it to boot to the user config or to download a new configuration. If you plug in the board into a dumb power supply, the bootloader will detect that it's not connected to a computer and it'll automatically reboot into the previously loaded user configuration.
Oh, nice. Okay. And then it's just doing what it would normally do.
Yeah, exactly.
That's great. So that kind of shows the power of having that flexible fabric in the first place. Is it possible to pull that USB integration into future designs as well? Like, can people have a USB interface to a computer for their designs?
Yeah, so it's all open source. They can reuse it and distribute it. I think it's under GPL 3 right now.
Okay.
and I'm using it. I've ported it over to a Xilinx board, and then I'm also using it on my EX boards. So the EX prototypes that I have back have the bootloader running, and something cool that I was able to do. So I had going to the BX. I also rewrote a lot of the bootloader, and I fixed a bunch of bugs, and I cleaned up the programmer, and I added a new capability. So every FPGA board that uses this bootloader can store information about the board in the SPI flash, and it's called metadata, so that the programmer application knows where the bootloader goes if you're updating the bootloader. It knows where the user configuration goes, and it knows exactly what data and what addresses in SPI flash are usable for the user for their own data, like storing, instructions for their CPU to execute.
So it's kind of like a map file, but for the SPI flash?
It's like a map file, as well as identifying information about what the board is, as well as a unique ID. So if you have multiple of these boards plugged in, you can see all the boards that are plugged in, and you can see their IDs. So, which is kind of important if you're doing different projects, because you don't want to accidentally flash one board with the wrong bit stream. So you can specifically say flash this board with this ID.
Interesting.
And then the next step forward that I want to do for that is add either the data within the SPI flash itself or a link to a web page, so that tools like iStudio can automatically pull in the configuration for your board and use that in iStudio, even if iStudio itself doesn't know about your board. But because your board provides that data built in, iStudio can use that, and you can start running with it immediately. And that wouldn't work just for iStudio. I also want to enable that for APIO and any other tool to be able to just plug in the FPGA board and get all the information that tool needs to work with that board.
Man, there's a lot to learn here, huh? Are there other resources that, how did you get into all this stuff?
Boy.
I guess you had some background in it, huh? We didn't really talk about that either. But
like for FPGAs in general,
yeah.
I never used them professionally.
Okay.
In college, I had bought a board from Xess, XESS.
Dave Vandenbout, who's been on the show before. Twice.
Yes. And that was my first FPGA board. And it was like, it looks like a gigantic version of my boards today, because it was dual inline PCB. On one end, it had a parallel port, and it was barely wide enough to fit the parallel port.
Oh, this is an early one. I was going to say, because the new ones with the Spartan 6 are not that big. So you're saying like Dave's early boards.
Yeah, this was a Spartan 3 1000 something or the other. And on the other end, it had a VGA connector and a PS2 port. That was that was my first board, and that was awesome. And I had just played around with that. And then when I got into my digital logic class in college, I did more with one of the Digilent boards. And then I just have been collecting FPGA boards and now developing my own FPGA boards.
Next thing you know, man, you start making your own FPGA chips, and then it's all over. Then you start. Yeah. Then you'll just start. Then we'll just see you on a beach somewhere scooping sand into a bucket. We'll be like, "Look, what are you doing?" Like, "Oh, I'm starting a chip fab."
Yeah, I'm a
last thing to do.
I'm a full stack.
I'm gonna hang out. Yeah,
full stack developer.
Yes, that's right. You ain't full stack until you're making your own chips.
Yeah.
Oh boy. Okay, so but you're saying that learning wise, it was mostly just tutorials and understanding tool chains and stuff over time. Yeah,
so I had found out about iStorm actually after I designed the B2 board, and I had even been selling them. I had kind of heard about it before, but I didn't pay much attention. So then I had took another look at it, and I just kind of fell in love with it because it the possibilities that it provides of having the open source toolchain and allowing people to remix and redistribute is very powerful. There is a professor in a university in Egypt that is working on a online IDE for working with FPGAs. Yeah.
Okay.
And so,
what's his name or her name?
I would have to go back and look. But with the iStorm tools, you could host that on your cloud servers, or you could even conceivably, put that and run it within the web browser itself. get from, plugging in the board to blinking in a matter of minutes. And make it very, very easy for people to get started and to use FPGAs.
Yeah, it's interesting with all the... man, that would be trippy, huh? I mean, I know that there's like web USB is like how... that's how Chromebooks talk to USB, and it's all JavaScript based, and I think that's right. But thinking about like that, then programming an FPGA, like going from like cloud level tools down to an FPGA is pretty trippy.
Yeah. Or even having this, another board design that I want to do at some point is a Wi-Fi enabled board.
Oh, cool.
And so you could program the FPGA over Wi-Fi.
You could just just drive an antenna directly with an FPGA, a high-speed FPGA pin, and see what happens.
Yeah. So the software-defined radio guys.
I'm kidding.
Yeah. The software-defined radio stuff, that is amazing, and it's magic to me. And the boards that have come out, like Lime SDR and others, are just beyond my abilities. I don't think I could make a worthy SDR.
I think that stuff paired together is kind of interesting though, because so obviously Mike Osman has been on this show a lot, and like HackRF and a lot of the Great Scott Gadgets tools, they are peripherals, right? So thinking about, they are USB peripherals where they're pushing data from a software chain down to the USB, and they're streaming data back and forth. So in theory, I mean, if you hook those things together, it could be interesting, but maybe I'll make some intros after the show.
Yeah, there are FPGA boards for software-defined radio. So you can do a lot of that processing in the FPGA. I'm not familiar with it myself, but I've looked at them and they're gorgeous.
Yeah, well, I mean, I think that's really where, at the beginning of the show we were talking about the way I always think about it is streaming, right? So streaming data back, high-speed data through a thing, and then doing some processing on it in line. You called it something else. What did you call it?
Like a pipeline, right?
Pipeline, yeah. So it's like you said, pipeline versus logic or versus control. So like pipeline data like that is where FPGAs are just killer. Like Derek Kozel has been on the show too, right? And he talks about that stuff too. And being able to, Matt Edis is another one who's been on the show. So like all these people, they're often working with FPGAs. I think that the SDR folks, like Osman, like they got a lower cost by not doing FPGA stuff. But I think that the accessibility and the dropping costs make some very interesting future options.
Yeah.
Cool. So Luke, where can people find you now that Maker Faire is over? Are you going to any other conferences?
So I would like to do the Hackaday Super Conference that I think is in November.
That's right. Yep. I've heard rumor it'll be the first weekend of November.
Okay. So I want to do that, and I've been toying with the idea of doing a workshop.
Okay. Cool. Yeah.
Which would be pretty cool. We'll see though.
Okay. Yeah, that'd be great. That'd be really great. Where can people find you online? And more importantly, where can people buy a BX board or any other boards, really? So
if you go, there's two places. I started on Tindy. Okay. And so Tindy was an awesome way to start selling things with a community of people that are, really enthusiastic about hardware. So you can go to Tindy. You could just search Tiny FPGA Tindy, and you'll find my Tindy store. And you can get the A-series boards there and the programmer there. Okay. Once the BX crowdfunding campaign is over, then you can order the BX from Tindy or my own web store. But today, if you want to pre-order the BX, you can go to crowdsupply.com/Tiny FPGA, and then you should see the project there.
Wait, is this not out yet?
The BX?
Oh yeah, I thought. I'm sorry, I thought it was out already. I'm an idiot.
It's almost out.
It's almost out, right.
Yeah.
But I didn't even look at the date. So it's funded on April 19th. So it's like in the throes of shipping and programming right now, huh?
So right
Ships
now,
July 16th. The list says, I don't know, it's coming up. Just saying.
Yeah, and that's gonna get pushed out a week, I think.
Oh, no.
The FPGAs were supposed to be shipped last week to the manufacturer, and the last I heard, it's delayed until tomorrow. And so tomorrow I'm going to find out if they're actually getting shipped or if they'll get delayed again.
Got it. Okay, so the B2 exists and is out in the world, but you're saying that was a limited run. That's why you can't buy those right now. So the idea is that people could go and buy a BX and have one on the way.
Yeah.
Okay. Cool.
Yeah.
Free
so
shipping, $38 for your own BX, huh?
Yeah. And
Cool.
I've offered on the crowd supply. You can get pretty nice discount depending on how many you get. And I put in one for 25 boards, and I didn't expect anybody to buy it. But I think I've had two or three.
The classroom bundle? Yeah.
Yeah, I've had 2 or 3 people buy that, which was pretty cool.
Well, this is very exciting. I'm excited. I'm going to probably buy one right now. So
Yay.
so people can go and buy more. Do you have enough? Are you going to build enough that if there will be stock past the crowdfunding campaign?
I don't want to run out of stock again. So I ordered 1,250 boards.
Oh, okay. You got some room, huh?
I've sold almost half of them now.
Whoa, nice. Okay.
So with the lead times of components in manufacturing, I need to put in another order really soon.
Yep. Wow, that's crazy. Okay, where can people find you on GitHub, Twitter, everywhere else?
So if you just search for Tiny FPGA with no spaces, I'm there on Twitter as Tiny FPGA. I am at GitHub as Tiny FPGA. I'm on Hackaday as Luke Valenty. You can go to tinyfpga.com and catch me at the forums.
Okay, that's great.
Yeah.
Cool. Well, Luke, thank you for being on and telling us about this stuff. I'm excited to try this out. I think that your enthusiasm around this project is very well founded, and I think that the FPGA future is racing towards us. So we'll see.
Yeah. Well, thank you very much for inviting me. This was a lot of fun.
Okay, we'll talk to you soon.
Great. Thank you.